Hello, this is Mr. Sand again, and we're going to be talking about more second law problems. Specifically, the elevator problem. In an elevator problem, every elevator problem's the same. You start off with some dude in an elevator. And so here's an elevator. There's a little cord that's connecting it. Okay. Now we've got a scale that some dude is standing on, and then he's always standing on a scale. Here's a guy, kind of. He's got little circles for hands, and he's happy. Oh, look at that, he's happy. And he's a little confused why this is happening to him. So I always use Carlos. This is Carlos, and he's on his elevator, and he's an elevator attendant. He's always standing on a scale, and the scale right here has a little reading, and it's telling him something. Now, normally, when you just have at a rest kind of situation or uniform velocity, you have some things that are always true. You have the fact that Carlos is being pulled down here. So I'll just drop in the middle of Carlos right here for his free body diagram. We're just considering Carlos here, nothing else, just Carlos. So he's always got FG pulling on him, and like they've always got the normal force pushing back up. So supporting Carlos going upwards. Okay, that's the normal force. So if he's just standing, he's got normal force coming up and a gravitational force going down. Now the normal force in this case is provided by whatever he's standing on. So in this case, it's the scale. And the scale, I don't know how much you really want to know about this, but the scale normally has some sort of a pressure sensor, like a spring, and these old-timey kind of analog scales. I'm sure you've seen those things that kind of they swing back and forth when you step on them. They have some sort of a spring that determines the force that's being exerted on them. So in this case, right here, the spring is pushing back up, and that spring is calibrated to show Carlos right here how much force that it's pushing back up on Carlos. So that force is the normal force. So Fn is how much the scale reads. This is the scale's reading. So whenever you're in any of these kinds of elevator problems, just know that Fn, the normal force, is what the scale's reading. It's the force that's pushing back up on Carlos in this case. It's also known as the weight of Carlos. But now we're going to do something funny. The reason why we're putting this in an elevator is because now we're going to accelerate this up and down, and we're going to see how the weight changes depending on this whole elevator accelerating up or down. Okay, so we got this whole scenario set up. I hope this makes sense to you right now. I'm just going to leave this drawing right here, and we're going to go through a couple problems. First, I just want you to think about this. Now, think about riding in an elevator. Let's say that you're starting off, I don't know, like at the basement of a building, and then you're going upwards. So when you're going from the basement upwards, do you notice what it feels like to stand in an elevator when you first start off that trip in an elevator? Let's say it's a really quick elevator. What do you feel? Does it feel like you're being pushed up? It should. It should feel that you are kind of like heavier. Like your legs they have to support more. They have to do more work to support your weight. So it should feel like you're kind of pushed down as you're accelerating upwards. And that's right. And then when you're at the top of your journey, wherever you're going, you might feel a little bit lighter. In fact, I used to do this when I was little, and sometimes now still. I just went to the observation deck of the World Trade Center, and it's really cool. You should go. And at the very top, I jumped, and it felt great because I was actually accelerating downwards, or the elevator was accelerating downwards, even though I was still moving up, and so I was lighter at the top. So at the top, it should feel like your legs have to do less work to support your body. And so it seems like there's less of a force at the top. So I hope we have that clear. At the very bottom, and you're going upwards, you should feel heavier. And at the very top, when you're slowing down up there, and you've gotten to the top of your journey, it should feel lighter. You should feel lighter as you're going up, and then slowing at the very top. Likewise, if you drop in an elevator, like right away when you drop, let's say you're at a high level in a building and then you drop, then you should feel lighter. And at the very bottom of that journey, when you're slowing down and you're at the bottom near the basement, after you've been going and slow, you should feel heavier too. So I hope that all makes sense to you, because we're going to work forward from those kinds of intuitions. Think about this every time you go in an elevator. All right, so let's look at the elevator problems. These are always difficult to set up, so I'm going to give you an easy way of setting it up for every single time, and it will always get you the right answer, and you'll love it. So let's look at Carlos ones. Carlos steps into a scale inside an elevator. This is in your workbook. I'm not sure exactly what page it is in your workbook. I'm working with an older copy right here in my hands, but it's the one with Carlos, and he's got an elevator. He's in an elevator, and his mass is 74.1 kilograms. It says, draw a free body diagram to keep these questions clear. I hope it's clear. A, what is Carlos's weight? Remember what weight is. Weight is the normal force. If the elevator is traveling at a constant velocity. Well, if it's traveling at a constant velocity, let's just look at what this would look like. So I'm going to say this is 3A, I believe. So if he's at a constant velocity, for every one of these problems, I'm going to say the sum of all the forces will equal, well, what are the forces involved here? We've got Fg and we've got Fn. So in a scenario where he's traveling with a constant velocity, this could be just resting. That means that the sum of all the forces will be 0. So we know that that's 0. And we want to know what his weight is, so we'll solve for this problem for Fn. So this will equal Fg plus Fn. If we want to solve for Fn, all we do is take 0 minus Fg, and that will equal our Fn. In this case, our Fg is the gravity here. This will equal minus m times gravity. That's acceleration due to gravity. So this is going to be Carlos's mass, which is 74.1 kilograms, times the acceleration due to gravity, which is negative 9.81 meters per second squared, and this will give you Fn. So if you multiply these things together, you'll get a positive number, which should make sense to you. His normal force should be positive. You'll get as a final answer 727 newtons. Okay, this is the easy scenario. Now, the key thing to think about here is that this whole scenario, the sum of all the forces will equal 0 because he's not accelerating. In this situation, he's not moving, or he's moving, but it's at a constant velocity, so there's no acceleration. So that's this scenario, 3A. Let's go to 3B. It's a little more difficult. It says, what is Carlos's weight if an elevator is going up but is slowing at a rate of 1.28 meters per second squared? So let's set this up again just without thinking. We always go to the sum of all the forces equals Fg plus Fn, and we're wanting to find Fn. All right, well, the sum of all the forces here. The sum of all the forces means that is all the forces that are summed up on Carlos. And the result, well, this F right here is going to equal ma. And what it's saying in the problem is that this sum of all the forces is going to have an acceleration which is 1.28. And it says slowing at a rate of 1.28. So if Carlos is going up, so he's going upwards, that's his motion, he's just going upwards. This is not a force right here, it's just his motion, he's going upwards. And he's slowing at a rate of 1.28 meters per second. That must mean that the acceleration is a downward direction compared to what his motion is. So I'm going to consider this acceleration to be negative. I hope that makes sense. He's moving upwards, but his acceleration is going downwards, meaning he's not accelerating upwards, he's actually accelerating downwards so that his motion will go to 0. So this is going to be his mass, whatever Carlos's mass is, times Now I'm going to put in this negative 1.28 meters per second squared. That is the sum of all the forces is going to equal that, because that's what his overall motion is. So this equals Fg plus Fn. If we want to solve for Fn, which is we do, it's going to be m times negative 1.28 meters per second squared. And now this is going to be minus, now Fg I'm just going to replace with this times negative 1.81 meters per second squared equals Fn, right? So I'm solving for Fn here. So here's Carlos's mass is 74.1 kilograms. I'm just going to plug that into here and to here, 74.1 kilograms. And I'm going to get as a final result here what his weight is. His final result is, should get a positive number here, should be 632 newtons. That's your result. And that, notice that it's different than this. He's lighter here. That force is less than this, meaning that he feels lighter. The scale does not push back as much. And that should make sense. That if you are accelerating downwards, you should feel lighter to the scale. Okay, I hope this makes sense. Now, do the same kind of procedure, which is doing the sum of all the forces equals Fg plus Fn for 3c. Wait, I'll do that very quickly up over here, and then it should make sense from here on out. This takes time, takes practice, so be patient with yourself. So the sum of all forces will equal Fg plus Fn. Now the sum of all the forces here will give you, for C, it says he's going down but is slowing at a rate of 1.59 meters per second. So he's going downwards, his motion is downwards, but his acceleration's up, so it's a positive number. So it's going to be his mass times 1.59. Okay, and equals Fg plus Fn. Now I'm going to subtract Fg on this side, so it's going to be m times 1.59, oh I didn't put the units in, meters per second squared, minus his mass times negative 9.81 meters per second squared, and this whole thing equals Fn. I ran out of room here, but it equals Fn, so I'll just write equals Fn on this side. Okay. So if you put it in Carlos's mass, which is 74.1 kilograms, you should get as an answer for C, 845. This is rounding with sig figs, newtons. And he feels heavier as he's going down and the elevator's slowing. That should make sense to you. Okay, let me know if you have any questions. That should get you started. Good luck.